Hi everyone, thanks for watching my YouTube channel where I teach. Before we get started, this video is sponsored by absolutely no one, but Quick Trip. If you're up for sponsoring me, I will gladly take whatever freebies you're willing to send me. This week we talked about ratios and proportions. A ratio is a comparison of two quantities, which of course begs the question, what is a quantity? Well, it's pretty much anything we can measure or count. So basically it's a number or a value of some kind. We can write a ratio as A to B with a colon separator, or like a fraction A over B. Some examples of ratios would be miles per gallon, which compares the distance driven, which we measure in miles, to the gasoline used, which we measure in gallons. We can also have a student-teacher ratio, which compares the number of students to the number of teachers, both of which are quantities we can count. And if you're in band or you just know a lot about music, you might have heard of beats per minute, which compares a countable quantity, the number of beats in a song, to a measured quantity, the amount of time elapsed in the song. So you can see from these examples that a ratio can be two measured quantities, two counted quantities, or it could be a mix of both. So that leads us to the next question: what is a proportion? Well, it's just two ratios that equal each other. For example, A over B equals C over D. We have four properties of proportions we're going to cover in this video. First, if two ratios are equal to each other, then their cross products are equal. So that means I can multiply B times C and A times D, and I'll get two numbers that still equal each other. Second, if two ratios are equal to each other, then their reciprocals are equal. That means I can flip both of these fractions and still have a true statement. Third, if two ratios are equal to each other, their means can be swapped. The means are the two numbers in the middle of the proportion, so in this case, B and C. So I swap B and C around, and this proportion is true as well. Finally, if two ratios are equal to each other, then their denominators can be added to the numerators. So if A over B equals C over D, I can add B to the numerator on the left side and add D to the numerator on the right side, and we still have equal ratios. Now, the reason that we spent 2 days on ratios and proportions was because of how they apply to similar triangles. Let's talk about similarity. The last unit was about congruence. For congruent triangles, corresponding angles were congruent, so the triangles had the same shape. Corresponding sides were also congruent, which gave the triangles the same size. And when we wrote out a congruence statement, like triangle ABC is congruent to triangle DEF, we are saying that angles A and D were congruent, angles B and E were congruent, and angles C and F were congruent. We could prove triangles congruent using side, 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 angle, angle, side, angle, and hypotenuse leg. What we could not use was side, side angle and angle, angle. For similar triangles, we're still going to specify that corresponding angles are congruent. But now, corresponding sides are proportional. So the triangles don't have to be the same size. We're going to write our similarity statements the same way we wrote congruence statements. So when we write ABC is similar to DEF, we're still saying that angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. We really only have three theorems we care about for similarity: side, 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 and angle, which we'll get into in a moment. We can still use hypotenuse leg, but that's less common. And we still can't use side, side angle. For angle similarity, if two angles in one triangle are congruent to two angles in another triangle, then the two triangles are similar. Now, one way that they might give this to you is by giving you a pair of angles that match, in this case the two that are 135 degrees, and a pair that doesn't. in this case 15 degrees and 30 degrees. But in the triangle on the left, we can find the unknown angle by subtracting the known angles from 180. So 180 minus 135 minus 15 equals 30. So we actually do have two angles in the triangle on the left that match the triangle on the right. We could do the same thing to find out that on the right the missing angle is 15 degrees, but that's why we only need two angles. If we know two of them, then we know all three. So we don't have to check the third once we've established that we have two that match. These two triangles are similar. Another way that they could show you angle-angle similarity is just by marking the two pairs of congruent angles. They could also just mark one pair of angles, but then give us a pair of vertical angles which we could mark congruent ourselves. Our next similarity theorem is side-side-side similarity, which states that if all three sets of corresponding sides are proportional, then the two triangles are similar. For example, here, we would say AB over DE equals BC over EF equals AC over DF. Notice that in this proportion, all the side lengths on top come from the same triangle, and all the side lengths on bottom come from the same triangle. Also notice that each individual ratio is made up of two corresponding sides. For example, AB corresponds to DE, BC corresponds to EF, and AC corresponds to DF. So because each ratio of side lengths is equal, the two triangles are similar by side-side-side similarity. The last theorem we're going to cover is side-angle-side similarity. If two sets of corresponding sides are proportional and the included angles are congruent, then the two triangles are similar. So what we would need here is AB over DE equal to BC over EF, and angle B congruent to angle E. Now it didn't have to be those two sides specifically, I just picked them because I felt like it. But we still have the same rule we had for side-angle-side congruence. The 1A is touching both S's, so the angle I use has to touch both of the sides that I use. So once I picked AB and BC, I was locked into picking angle B. And again, notice that each ratio has a pair of corresponding sides, and the numerators all come from one triangle, and the denominators all come from the other triangle. So that's week 6. Big thank you to Quick Trip, not for sponsoring this video, but just for having awesome fountain drinks and personal pizzas. If you want to send me some freebies, you don't even have to pay for shipping. I live in Tulsa. I drive by your headquarters all the time. I can easily make the drive to 51st and 24th to pick them up. Seriously, Quick Trip, DM me.